Okay, so hopefully I got the audio working on this. So what we're going to do here, guys, this is the option. Okay, now we're not doing option 2, which is applied electricity, because it's very long, very theory heavy, and nobody really does it. Everyone does particle physics because it's a lot easier. Okay, all right, so this topic is quite long. It's 17 pages in total. So what I'm going to do is I'm going to split the video in two. Part 1, I'm going to go from page 1 of the notes of topic 31 all the way up to page 9, which is pair production, pair annihilation. Okay, then the next video I'll put up, part 2, we'll do particle accelerators all the way through to the to the quark and the anti-quark composition. Okay, so for this, guys, as you've seen in the other videos, there's a quick recap at the start. I'm just going to skip over that because go back over the videos. You should know this, just a recap for yourselves. So conservation of momentum in a reactor. As we've seen in previous topics, many elements are naturally radioactive and their nuclei undergo changes when they undergo radioactive decay. All right, so the net amount of electrical charge before the reaction. Okay, so where are we now? The net amount of charge after the reaction, okay, must have the same as the electrical amount of charge before the reaction, okay? Because obviously energy is constantly released. This disintegration energy here, we're just going to give it a symbol of Q, okay? And of course, it has to be conserved. Now, if in an exam, what is conserved in a nuclear reaction? Mass to energy ratio is conserved, momentum is conserved, and electrical charge is conserved. They're all conserved. So the mass energy ratio is conserved, the momentum is conserved, and the electrical charge is conserved. Okay? All right, so problem 1 is pretty much the exact same as the previous question, no new things here. So we're just going to fire through this fairly quick. We have an alpha emitter and it disintegrates as follows. Find the energy released of Q, or sometimes E, it could be given as E as well, between the daughter nucleus and the alpha particle. And they gave us the masses as such. Okay, so as always, mass of reactants. First, what are our reactants here? It is uranium. So the mass of the reactants, 3.9528333 by 10 to the minus 25. What are our products? So mass of products underneath. Well, our products are the other two values, thorium and helium. So add the two of them together and we should, where's my calculator there? So I actually didn't add them together to get a number, I just basically left them and subtracted them one by one. So just to make it more easier, 886294 by 10 to the minus 25, 6294 to the minus 25, plus 6.64632 by 10 to the minus 27 gives us a value of 3.9527 by 10 to the minus 25. Okay, so we subtract one from the other. So 3.9528333 by 10 minus 25 minus, so we should end up with, so 7.578 by 10 to the minus 30 kgs. 10 to the minus 30 kgs. Okay? So again, we fire that into our equation. Now obviously it's a positive number. So a positive number means energy out because we lost mass. Okay? That doesn't really matter, but it's nice to know. E equals simply mc squared. C being the speed of light, 3 by 10 to the 8 to be squared. Put those in and we should end up with 6.8202 by 10 to the minus 13 joules. Give your answer in joules and electron volts. Okay. Or mega electron volts. Okay. So again, 1 EV equals 1.6 by 10 to the minus 19 joules. So therefore, to go from electron volts to joules, you multiply by charge of an electron. To go from joules to electron volt, we divide. Okay? So, because obviously 1 joule equals 1 over 1.6 by 10 to the minus 19 electron volts, you see? So you divide by charge. So what we do is it's going to be 6.8202 by 10 to the minus 13 divided by 1.6 by 10 to the minus 19. So our energy in electron volts will work out to be 4.26 by 10 to the 6 electron volts. Now it wants it in mega. Mega is by 10 to the 8. So therefore, no, actually I made a mistake. I think mega is 10 to the 6. This would be handy enough if I had my log tables with me. So apologies, I think I made a mistake. Let me actually look that up there quick off the top of my head. I'm forgetting it. So this is why it's handy to have your log tables, and I'm not confusing. Yeah, it's 10 to the 6. Yep, it is 10 to the 6. All right, so I made a boo-boo in the other video. So I'll have to actually change the other video. No, actually, yeah, I said 10 to the 8 in the previous video. Mega is actually 6. So I'll have to redo that whole video. Okay. So there you go. 4.26 mega electron volts. All right. So what is the neutrino? So what they actually found, this thing, Wolfgang Pauli, the reason he discovered it was that when he tried to measure the momentum, it turned out it wasn't actually conserved. Okay? So they found that the momentum wasn't conserved before and after, which means something must have been wrong. Okay? And that's why he ended up discovering the neutrino, because it's extremely small and has almost no mass. Okay? And it has 0 charge. So it's extremely small, close to 0 mass, and no charge. So of course they missed it. Okay? But by throwing in the neutrino, we now could resolve it, because now it made up for the fact that momentum wasn't conserved. Now it was, after equals before. Okay? Now what they'll ask you is, why is it hard to find it? And the answer is this. So why did they find it? Is because, well, they realized that it wasn't conserved. Why? So they had to look into it, and when he did, he discovered the neutrino. It's uncharged, small mass, and barely reacts. Okay? Alright, so this question here, absolutely horrible, but we'll go through it. So the reaction, okay, between these two particles, 7.8 by 10 to the minus 13 joules of energy are released, as kinetic energies of the products. If the ratio of the masses is 200 of the products of the product masses of the products is 222 to 4, find the kinetic energy of the alpha particle. Okay, so there's two ways to actually approach this. Okay, one way that I'm going to do is I'm going to look at the momentums between the two and get the ratios of the momentums and solve it from there. The others is compare the kinetic energies, divide one to the other, and solve it that way, and I should also be able to solve it as well. Okay, but I'm going to do the momentum one. So basically, momentum before has to equal momentum after. So basically what we have is we have RA here, and then afterwards it splits into two particles, Rn and He, and they go off in opposite directions to keep the momentum the same. And obviously this is going to get 222 times, and this is going to get 4 times the mass. Okay, so this Rn gets 222 parts of the original mass, and the helium only gets 4 parts, if you imagine it that way. Okay, that's the ratio. So our momentum here, momentum before equals after. Okay, so that was not a great time for this pen to stop working. So before equals after. Okay, so before is 0 equals after which is also going to be 0. But we know after is the mass of one object, and we call it U, and the mass of the second object, and I'll call that, well, I could call it U2 actually. Actually, we call them both, to be correct to the equation, V1 and V2, okay? And in order for them to be equal to 0, that should not be a plus, that should be a minus. Why? Because they're going in opposite directions, okay? So I'm going to make M1 the Rn, so I'm just going to call it R, to make it easier, and I'm going to make M2 the helium. Okay, I'm going to have to put them in right, because if I don't, it's going to just look wrong. All right, so now to get rid of the minus, okay, we bring one value to one side and the other value to the other side. So we could also just rewrite this as, therefore, MRN, VRN equals MHE, VHE. So I'm going to take the M's to one side, the V's to the other. So I'm going to have M or N over M HE equals V HE over V or N. Now we were told that the ratio of the masses is 222 to Rn and 4 to RHE. So I'm going to rub out the top bit here now, guys. Okay, so I'm going to have to rub the whole thing out. So rub the whole thing out. I'm going to split my page in two just to try and, all right, so you can always go back over the video to find out. All right, so therefore, good, the pen has stopped working. 2 over 4 equals V of the hydrogen over V of the radon or Rn. Okay, so can we divide that even further? 22 divided by 4. Okay, so this gives me a nice clean number. 55.5 equals, in other words, 555.5 of the helium is equal to, all right? So in other words, 55.5 goes to the speed of the larger of the two. No, sorry, I'm wrong, yeah. So this, okay, is the same as 55.5 times of the VHE, okay? So in other words, our ratio here is, 55.5 to 1. So 55.5 to 1, okay? Now that makes sense, all right? So radon is getting, it's not radon, it's Rn. I'm going to call it Rn because I can't. I'm having a brain fog moment again. But basically, it's getting, okay, it's got a larger mass. So therefore, in order for the momentum to be the same, the helium has to be moving faster, okay, to make up for that momentum, the lack of mass. Okay, so that's our ratio of 55.5 to 1. Okay, so we were told the total energy. So the total energy is, what do we say, 7.8 by 10 to the minus 13 joules. Okay, so there are 56 parts. Why are there 56? Because the ratio is 55.5 to 1, which means it has to be divided into 56.5 parts. So therefore, so 1, we'll say, equals 7.8, not 88, apologies, 7.8 by 10 to the minus 13 divided by 56.5. And then, so we want to find out, what's the question? If the ratio, find the kinetic energy alpha particle. So we want to just find the alpha particle. Okay, so we want to find the kinetic energy alpha particle. Well, the alpha particle is getting 55.5. Okay, so that's how much the alpha particle is getting. So we just simply multiply that then. So 55.5 equals 7.8 by 10 to the minus 13 divided by 56.5 times 55.5. Okay, so therefore the alpha particle should receive, let me see now, what did I get? should receive 7.66 by 10 to the minus 13 joules. Okay? 7.66 by 10 to the minus 13 joules. Okay. So again, you could do that another way, but I found this way was just easier. Okay, so this is very important. It's important because obviously it was a big step for science. It's also important because in the exams they will ask it. Okay, so the first artificial splitting of a nucleus by artificially accelerated particles. Okay, so what we have here is you have your particle accelerator. The protons are produced up here in the top, and they go through a high potential difference. Okay, and they slam into the lithium target. Okay, and then of course on the zinc screens here that you get little dots. Okay, little dots start to appear, and this was the first artificial splitting. Okay, this is the first time they actually did it. Okay, so these two are the two that did it. Which one? I think one of them is Irish. That's why they kind of ask this quite a lot. So make sure you know them. So the operation. So protons are this is literally your operation. Protons are released at the top. They get accelerated across potential difference. Just say a high potential difference, but 800 kilovolts. But a high potential difference will be fine. The protons collide. Okay, and two alpha particles are produced, and they move in different directions. Okay, so basically this was a big revolution. Okay, because when they saw that the dots appeared, they both appeared at the same time in opposite directions. In other words, going off. Okay, splitting. All right. It is important to remember that it's mostly empty space. This is key. All right, I think this was asked before. All right, so most did not collide with the nucleus. Okay, so the majority just went straight through the lithium, which of course reinforced the idea that atoms are mostly empty space. Okay, this is the equation you need to know, but it's fairly straightforward if you just remember. So we have protons, which are hitting a lithium screen. So go to your log tables, and a proton is of course mass 1, charge 1, and lithium is 7.3. Okay, and we know that it's going to split into two alpha particles. So just remember your alpha particles are 4.2, and kinetic energy. That's it. Okay, that's all it is. It's fairly straightforward. Okay, you don't even need to learn it off. Just remember, proton hits lithium screen and releases two particles. You should be able to figure it out from that. Okay, now the big thing, so the big thing here, why was this significant? Because it was the first artificial splitting of the nucleus. It was the first transmutation using artificially accelerated particles, and it's the verification of Einstein's E equals mc squared. Okay, and it was also the first particle accelerator used. So 4 very important things. Okay, so if you knew 3 of them, you'd be perfectly okay. All right, so know 3 of those. All right, and then of course here, verify E equals mc squared. Now the big one, the N unified atomic mass unit, or the unified, sorry, not that the N shouldn't be there. Okay, so basically what we're going to deal with now is you're going to be given, so all along they gave you the mass in kgs. So now they're not. Now they're going to give you the unified atomic mass units. Okay, that's what they're going to give you, the unified atomic mass units. All right, and they're what's in the back of the log table. So in the back of the log tables, when they give you the masses of stuff, it's not in kgs, it's in the U value. All right, so you basically have to multiply it by 1.66 by 10 to the minus 27 to get it converted into kgs. Okay, so you have to convert it over. Now I would advise waiting until you've answered a good proportion of the question before converting. Okay, so I'll demonstrate now the next question here. All right, so when lithium is bombarded with a proton, 2 alpha particles are produced. How much energy is released? Given the atomic mass of lithium, a proton and a particle are. So they're given to us in the U values. Okay, and that's their respective. So what you do, as always, okay, mass of reactants. Okay, so the pen has gone. Give me a second or no. I'll try and get this thing to work again. It seems to be. Here we go. Mass of reactants. So what are our reactants here? It's lithium, which is this one, and the proton, which is this one. Okay, so it gave it to us in order. So lithium, proton, alpha. So that's lithium, proton, and the alpha is the last one. So when I added the 2 of them together, I got 8.02383U. So the mass of the products then is this times 2, okay, because there's 2 of them, don't forget that, which is 8.0052 U, and that gives me a value of 0.01863 U. So obviously the mass is lower, so energy emitted, okay? So now when I'm here, I convert this to kgs, so therefore the change in mass is 0.01863 times the U value. Again, it's in the log tables, 1.66 by 10 to the minus 27. So my change in mass should work out to be 3.00926 by 10 to the minus 29 kgs. E equals mc squared, c being 3 by 10 to the 8 squared, which gives me 2.78 by 10 to the minus 12 joules. And there we go. Okay, so leave it in the U value until you get your change in mass, then multiply it in. Okay, much easier, less messy, less room for mistakes. Always do the easy option. Okay. All right, so calculate the energy in both joules and mega electron volts released in the following reaction. Okay, so uranium goes to thorium and helium, given that the atomic mass of uranium, thorium, helium are as follows. Okay, so again, the exact same mass of reactants. Ooh, wait, what happened there? Or CT. And our reactants are just uranium, which is this by itself. So 238.0507884 U. And the mass of the products, which is this plus this, which gives me 238.0461996 U. And I got a value of, no, sorry, hang on a minute, it's incorrect. No, I'm right, yeah, apologies. Okay, so I got my answer then to be 0. When I subtracted them, 0.00, Pentagon again, 4, here we go, 588 U, 0.004588 U. Multiply that then to get the change in mass is going to be that value, 0.004588 by 1.66 by 10 to the minus 27. Okay, and that gives, my God, this thing is getting worse. That gives us 7.61608 by 10 to the minus 30. See, we're now in kgs. So now we sub that in. E equals mc squared. And we should end up with 6.854 by 10 to the minus 13 joules. And I just noticed there the question asked for joules in electron volts. So we divide that by charge of an electron, which gives us 4.28 by 10 to the 6 electron volts. So there are our two answers. Okay? All right. So each particle has its own antiparticle. So every particle out there, every action is an equal opposite reaction. So every particle has its own antiparticle. Okay? An antiparticle has the exact same mass but the opposite charge. Okay? So the antiparticles are opposite to that of the particle. Okay? So if you're positive, it's negative. If you're negative, it's positive, etc. Okay? So you've got the positron. Okay? You've got, and this is very key to understand how to answer these, they have the same mass, same size, okay? Opposite charges, okay? Electron is matter, positron is antimatter, okay? And they spin oppositely, okay? So there are the three key things, because they'll often give it to you and people will say, well, they never gave me the mass of the antimatter or the positron. They did. It's the exact same as the electron, okay? All right. Of course, it was proven mathematically, okay? So it was proven by Paul Dirac. Again, apologies for destroying his pronunciation. He proved it before it was experimentally found. Okay, and generally these are their symbols. An antiproton is P with an N, a dash over the top, and the anti-electron is just E plus or E with a dash. I often write it as E plus. I just find it easier for some reason. Okay. All right. So pair production, pair annihilation is the last we're going to do for this video. So pair production, pair annihilation. You need to know them. So pair production is the creating of a particle and its antiparticle from electromagnetic radiation or gamma radiation. So basically what happens, the gamma ray comes in, it strikes the nucleus and it fires off an electron and a positron. Okay? So the reason for that, the charge before is zero. Well, not zero. The charge is neutral charge. When it strikes afterwards, it's also neutral because the electron is negative, the positron is plus. Momentum is also conserved because note, they do not move off in opposite directions. That's because the gamma radiation does have momentum beforehand. So if they moved off in opposite directions, you wouldn't have momentum after, which makes a problem. So how do we write this? Simply, gamma is equal to E minus plus E plus kinetic energy. Okay? And as I said, conservation of charge, the gamma ray has no charge, therefore before and after is zero. Momentum, the gamma ray does have momentum. Okay? So they do not move off in opposite directions. Okay, and the kinetic energy is of course seen by the particles moving away. So kinetic energy is conserved. Now, key, pair production can only occur if the photon has an energy exceeding twice the rest mass of the electron. In other words, when this gamma ray, why did that happen? When that strikes the nucleus, it has to have twice the size. Okay. Twice the energy to exceed twice the rest mass of an electron. Can you tell me why? Why does it need to be twice the rest mass of an electron? Have you guessed it? Because it's creating an electron and a positron, and they both have the exact same mass, so therefore they need to be double the mass of an electron in order for two things, the same mass of an electron, to occur. Okay? The next one, and that's kind of what it looks like. The particle goes up, strikes, and you see the two spinning off in opposite directions. Okay, pair annihilation. However, if we get an electron and a positron and we slam them into each other, we get this. E minus plus E plus gives us 2 times gamma. Okay? 2 times the gamma radiation. 2 gamma ray photons come out of this. Okay? Why 2? Why is it in pair production we only had 1, and in this we have 2? Well, in this, momentum was conserved because the gamma ray photon was moving, thus the 2 particles moved off, not in opposite directions. In this, the positron and the electron are slammed into each other, traveling in opposite directions. So technically their momentum is 0 because they come at each other from opposite sides. So therefore, 2 gamma rays have to be formed to move off in opposite directions in order to keep the conservation of momentum. Okay? And also note the net charge is 0. Okay? And for momentum to be conserved, okay, the electron and the positron are moving in opposite directions, directly before to each other. Okay? And there you go. Also, gamma ray photons. I know I said photons there. I'm lazy. But in the exams, please do say gamma ray photons to be physically correct. Okay, so we will leave it there after that. That's part 1. And we'll do part 2 next. And hopefully the audio is fixed. I know I had issues with the previous videos. All right, all the best. Leave any questions or comments below.